Hello. Reed-Solomon codes are the last topic in this course. Reed-Solomon codes are a family of BCH codes with parameter m equal to 1. Among other features, they have excellent burst error correcting capabilities. I'll define Reed-Solomon codes in lecture V7a and explain why they have excellent burst error correcting capabilities. In V7b, I'll present an alternative view of narrow-sense Reed-Solomon codes, which I will then use in V7c to describe an efficient decoding algorithm that works for all narrow-sense Reed-Solomon codes. Reed-Solomon codes were invented by Irving Reed and Gustav Solomon in 1960. A Reed-Solomon code is a BCH code of length n over g of q, where n divides q minus 1. In other words, Reed-Solomon codes are BCH codes with BCH parameter m equal 1. Here's a simple example of a BCH code. Let's take q to be 16 and consider gf2 to the 4 represented in the usual way. Recall that alpha is a generator of the multiplicative group of gf2 to the 4. We'll let beta be alpha cubed, so the order of beta is 5. So here we have q equals 16 and n is 5. Note that 5 divides q minus 1, so m equals 1. We'll now specify a canonical generator for a BCH code that is also a Reed-Solomon code. I'll take g of x to be the LCM of the minimal polynomials of 3 consecutive powers of beta, namely beta, beta squared, and beta cubed. These minimal polynomials are over g of q, so gf2 to the 4th. But the elements beta, beta squared, and beta cubed are themselves in gf2 to the 4. And so their minimal polynomials are just linear polynomials. For example, the minimal polynomial of beta over g of q is just x minus beta. This linear polynomial has coefficients in g of q, it's monic, and it has beta as a root. Similarly, the minimal polynomial of beta squared over g of q is just x minus beta squared. Multiplying these linear factors together gives us this cubic polynomial whose coefficients are in gf2 to the 4. We know from the theory of BCH codes that g of x is the canonical generator for a Reed-Solomon code of length 5, dimension 2, over gf2 to the 4, and its design distance is 4. Since g of x is itself a code word, and it has 4 non-zero coefficients, it has weight 4, and so the distance of c cannot be greater than 4. Hence, c has distance exactly 4. We can write down a generator matrix for c, this 2 by 5 matrix, whose rows are the coefficients of g of x, and x times g of x. So the second row is a cyclic shift of the first row. You'll notice that the entries of g are elements in gf2 to the 4, and that's because c is a code defined over gf2 to the 4. We can consider the code c primed you get by replacing each symbol in code words in c by its binary representation. For example, this is a code word in C. In fact, the first row of G. The code word is comprised of 5 symbols, each being in gf2 to the 4. I can replace each of these gf2 to the 4 elements by their binary representations. So, for example, the binary representation of alpha cubed is 0001. Alpha to the 11 is alpha plus alpha squared plus alpha cubed, which has binary representation 0111. In this way, we can replace code words that have length 5, but symbols in GF2 to the 4 by vectors of length 20 with entries from GF2. It's not hard to see that C primed is closed under addition and scalar multiplication over Z2. And so C primed is a binary linear code. It has length 20 because code words have bit length 20. Its dimension is 8. The code C has dimension 2 over GF2 to the 4, and so C has 2 to the 8 code words in it. Since C primed is a vector space over GF2 and has 2 to the 8 code words, it must have dimension 8. So to summarize, the code C prime we get from the Reed-Solomon code C is a 28 binary linear code. More generally, suppose that n divides q minus 1, and let beta be an element in GFQ of order n. Such an element exists because n divides q minus 1. Then the minimal polynomial of beta to the I over GFQ is just a linear polynomial x minus beta I. And this holds for all I between 0 and n minus 1. A Reed-Solomon code C of length n over GFQ with design distance delta is a BCH code of length n over GFQ with canonical generator g of x defined to be the product of the minimal polynomials of successive powers of beta from power a to the power a plus delta minus 2. Now g is itself a code word. Since g has degree delta minus 1, it can have at most delta non-zero coefficients, and so the weight of g is at most delta. Hence, the distance of C is also at most delta. By the BCH bound, though, we know that C has distance at least delta. Hence, we conclude that the distance of the Reed-Solomon code is equal to its design distance. Let's note that the dimension of C is n minus the degree of g, which is n minus delta plus 1. Since delta equals d, we have k equals n minus d plus 1, and so d equals n minus k plus 1. Now, for any linear nkd code, we must have that the distance is at most equal to n minus k plus 1. So Reed-Solomon codes satisfy this condition with equality. And so Reed-Solomon codes are optimal in the sense that for any fixed n, k, and q, with n dividing q minus 1, they achieve maximum distance among all nk codes over GFQ. One of the attractive features of Reed-Solomon codes is that they have excellent cyclic burst error correcting capability. Let me explain. Let C be a Reed-Solomon code of length n over GF2 to the r and design distance delta. Let's consider a code word C in the Reed-Solomon code. And note that each of the n symbols in the code word are elements of GF2 to the r. Let E be the error correcting capability of the code. So that's d minus 1 over 2, which is n minus k over 2, since d equals n minus k plus 1. Now, by writing each symbol ci in the code word as a binary vector of length r, we can view the code word C as a binary vector of length n times r. So here I have a code word with n symbols in it. Each symbol is in GF2 to the r, and viewing each symbol as a binary vector of length r, I can view the code word as a binary vector of length n times r. Now, if a code word C is transmitted, and a cyclic burst of length at most 1 plus e minus 1 times r bits is introduced, then at most e of the GF2 to the R symbols of the code word are received incorrectly. In this figure, the burst is among the shaded purple bits. The length of this burst is roughly 2R plus 2 bits. So it's fairly long, but it affects only 4 of the GF2 to the R symbols in C. Since the Reed-Solomon code C is an E error correcting code over GF2 to the R, these E errors can be decoded correctly. Let me collect what I just said in the form of a theorem. Let C be an NK Reed-Solomon code over GF2 to the R. Then C primed, the code obtained by replacing each symbol in code words in C by its R-bit binary representation, is a binary code of length nr and dimension k times r. This code has cyclic burst error correcting capability T, given by this expression. Here's an example. Let's consider the field GF2 to the 8 represented in this way. So this is a polynomial with coefficients in Z2 that's irreducible over Z2. The parameter Q is 2 to the 8, which is 256. One can check, although I won't do it here, that alpha has order Q minus 1. So we'll let beta equal alpha, and beta has order n, which is 255. I'll let g of x be the product of these 24 linear polynomials as the power of beta ranges from 1 to 24. So g of x is a product of the minimal polynomials of these 24 consecutive powers of beta over GF2 to the 8. Then g of x is the canonical generator for a Reed-Solomon code of length 255, dimension 231, and distance 25 over GF2 to the 8. The related code C primed that you get by replacing each symbol in each code word in C by its 8-bit binary representation is a binary linear code of length 2040, that's 255 times 8, dimension 231 times 8, which is 1848, and it has cyclic burst error correcting capability 89. I got 89 from this expression, with n being 255, k being 231, and r being 8. C primed has very high rate, namely 1848 divided by 2040, which is over 0.9. And it has excellent cyclic burst error correcting capability, namely 89. So when a 2040-bit code word is transmitted, then the receiver is capable of correctly decoding a cyclic burst error of length at most 89 bits. I'll conclude by mentioning that this Reed-Solomon code C and others derived from it have been widely deployed in practice, including in CDs, DVDs, Blu-rays, and in QR codes.
Here is an example of a QR code. As we saw in lecture V6G, the Gallet code is used to encode the format data. A BCH code is used to encode the version data. And a Reed-Solomon code is used to encode the payload. Here is the same QR code, but you can check that some pixels have been changed, from black to white, and some pixels to blue. Nonetheless, your QR code reader will be able to read the QR code even though it has errors, thanks to error-correcting codes. In V7b, we'll present an alternative view of narrow-sense Reed-Solomon codes, where the length n of the code is equal to q-1. We'll prove that these codes are identical to the ones defined in V7a. The alternative view is useful for describing a conceptually simple and efficient decoding algorithm for Reed-Solomon codes. See you later.